So how do we find the value for the limit of a function at a specific point? Well, there are a few techniques we could employ. Let's take this function, f of x equals x squared minus 1. Here's the graph for that function. Now suppose we want to find the limit of this function for an x value of 0. We can use the graph to see the value of f of x as x moves closer to 0 from the left or negative side. The limit on the negative side is getting closer to negative 1 as x increases towards 0. We can do the same from the positive side, and we get the same result. In general, as x gets closer to 0 from any direction, the function output gets closer to negative 1. When the one-sided negative and positive limits agree like this, then the value they both approach is the two-sided limit for the function, even if the function itself is not continuous and undefined at that point. In this case, the two-sided limit for our function as x approaches 0 is negative 1. Let's look at a more complex example. Here, the function is non-continuous and it's not defined for an x value of negative 1. Now from the negative side, as x approaches negative 1, the function gets closer to approximately negative 3.7. So that's our negative limit. From the positive side, as x approaches negative 1, the function gets closer to approximately negative 0.3. So that's our positive limit. Now when the one-sided negative and positive limits don't agree, there's no two-sided limit. So the limit for this function as x approaches negative 1 does not exist. Here's another function. This one's not defined for an x value of 0. We can simply create a table and use the function to calculate f of x for various values of x. So for x equals negative 1, f of x is negative 1 plus 2, which is 1. For an x value of negative 0.5, f of x is 1.5. Negative 0.99 plus 2 is 1.99. Now the function is not defined for 0, but we could use it to calculate a value just above 0. So for an x value of 0.01, f of x is 2.01. When x is 0.5, the function returns 2.5. And when x is 1, f of x is 3. Now if you examine that table, you'll see that the values returned by the function are converging on the same value as x approaches 0 from either direction. The value they're converging on is 2. Well, let's take a look at that on the graph. And sure enough, we can see that 2 lies on the line where x is 0, even though the function is non-continuous at that point. So the limit for our function when x is approaching 0 is 2. You can also find limits analytically by simply substituting the x value that you want to find a limit for into the function itself. In this case, we have a fairly straightforward function that's defined for every real number. To find the limit for an x value of 6, we can just substitute 6 into the function's formula. 6 squared is 36, and when we divide that by 2, we get 18. Now here's that point on the function graph, and you can see that it fits on the line where x is 6. This simple substitution approach works easily for our basic continuous function, but you can also calculate limits analytically for more complex functions using techniques like factorization and rationalization, which you'll see in the lab.